Let's use Riemann sums to compute an area. So what we're going to do is use the Riemann sums to calculate the area that's bounded by these given curves. The first curve, f, is the square root of x. The second curve is the x-axis. The third curve is the y-axis. And then the fourth curve is just the vertical line, x equal 4. And you can see that I have drawn a little picture here and shaded in the red to establish what actual area we're trying to compute. Now, in order to use a Riemann sum, we basically have to partition the interval that we're interested in. And the interval in this case is just 0 to 4, as I've written here, partition 0 to 4. So what we do is we just take n plus 1 elements that chop up, so to speak, the interval from 0 to 4. The first element obviously has to be 0, and the last element has to be 4. And any kind of subdivision will work as long as, in our particular case, as n goes to infinity, the subinterval lengths shrink down to 0. If we don't have that, then this type of technique doesn't work. So we're going to have that in this case, and I certainly don't want you to worry about that. But the way we've set this up, if we're going to use a Riemann sum, we will have to evaluate the function f in each of these subintervals. The first subinterval here from 0 to x of 1, the second subinterval from x of 1 to x of 2, etc. And so in order to make that really simple, we're going to choose right endpoints for our evaluation point. And that just means the c sub 1 will correspond to x sub 1. The c sub 2 will correspond to x sub 2, etc. That just makes the algebra easier, and all of our sums can start at 1 and again make the algebra simple. So in order to affect this, we're going to define a c sub I to look like this. That is, notice if I replace I squared with n squared, we just get 4. So if I is going to run from 1 to n, this will actually be a very good way to define c sub I. And then, of course, what about the c sub I minus 1? That is the evaluation point to the left of the c sub I. Well, we just replace I with I minus 1, and we get this. And then when we expand it, the I minus 1 is I squared minus 2I plus 1. Hit it with the 4, and we get 4I squared minus 8I plus 4 divided by n squared. Now, the nice thing about this is that as n marches off to infinity, the length of the subintervals gets smaller and smaller and smaller and converge to 0. So that's a good thing. Now, in order to get the length of the ith subinterval, because all these subintervals, will not have the same length, we have to do just a little subtraction. So that means we need delta x sub I to be c sub I minus c sub I minus 1. That's why I went ahead and computed this. Now when we subtract, we see the 4I squareds absorbed, and what's left is the minus minus here to give us the 8I, and the minus 4 to give us this. So we get 8I minus 4 divided by n squared. And then I went ahead and factored the 4, just to write it this way, 4 times 2I minus 1 divided by n squared. Factoring things always makes them easier to work with. Now, you're thinking, why do we do all of this? Well, the Riemann sum looks like this. That is, we have a sum from I equal 1 to n, where we evaluate the function f at the c sub i's, and we multiply by the length of the ith subinterval. So basically what we're doing here is just getting bunches of areas of rectangles. Very simple, but does require some setup. So we've done all the setup, and notice, in order to get the area, we want n to pass to infinity. That is, the rectangle widths will become so infinitesimally small that when we march them up through here, we won't be able to tell the difference. So this is the idea of using a limit of the Riemann sums to compute the red area here. Now, all we have to do is substitute. So we need f of c sub I. Here's c sub I right here, and f is the square root. So we take the square root of 4I squared divided by n squared. And then our computation for delta x sub I we've done right here, and we just fill that in. 4 times the quantity 2i minus 1 divided by n squared. Now, notice we have some simplification here. The i's and the n's are all positive numbers, and so when we take the square root here, we just get 2i over n, which you see right here. And then, of course, we have 4 over n squared times the quantity 2i minus 1. Now, there are things in here that don't depend on the I, so we don't need them to hang out in the sum. So we're going to factor the n cubed that we see right here, and we're also going to factor this 8 because they have no dependence on the I here, the index variable of the sum. So you can see now we factor the 8 all the way outside. It's a constant. It doesn't even have any dependence on n. And then, of course, the 1 over n cubed we leave right here. And that leaves behind what? An I times a 2i and an I times a negative 1, which gives us 2i squared minus I. Okay, so now the problem looks a whole lot easier. Now, of course, we're going to break up this sum into two pieces to use some of the famous summation formulas that you learned in pre-cal. And so, again, the 8 times the limit as n passes to infinity of 1 over n cubed. And then, of course, we'll factor the 2. So we'll have 2 times the sum I equal 1 to n of I squared minus the sum I equal 1 to n of I. And these are two very famous sums. I wrote in red here, famous sums. So this is why we like them to start at 1, because they're easy to remember. So this sum has the formula n times n plus 1 times 2n plus 1 divided by 6. And of course we have the 2 here, so we just move the 2 in. And then of course this sum, adding the first n counting numbers, is just n times n plus 1 divided by 2. Now, of course, now we have limits at infinity, which are really simple to do. Now, notice one thing here, the 2 over 6 will just be a 1/3. And then this n cubed we're going to multiply through. But what we're going to do is we're going to break it up. We've got 3 factors, and just break up the n cubed into 3 factors. So it's really easy to compute the limit. Now, here you can see that we'll have another situation here. And I left out my 2. I need to put the 2 there. So notice here I didn't bother to break up the n into 3, the n cubed into 3 copies of n, because notice the power of the n, the largest power here is n squared, so there's no need to worry about that. That's just going to pass to 0. So that's an easy limit. But again, I still need the 2 there. I mean, even though it goes away, we need to be correct. And so now when we look here, we have n over n, that passes to 1, that passes to 1, this passes to 2 and 1/3. So we just get 2/3 from this part when we let n pass to infinity. And of course here, when we look at the degrees, as I've said before, degree 2, degree 3, this passes to 0. And then we have the 8 outside that's been hanging out for the whole time. And so we just get 8 times 2/3, which is 16 over 3. Now, you're thinking, wow, that is a lot of work to do for an area. Is this what we have to do in calculus every time we do a problem like this? And of course it isn't. Engineers and physicists would be crazy, and even mathematicians. But what we've actually computed is what we say in calculus is a definite integral. And this is actually equal to the following symbols. This will be 0 to 4, principal square root of x dx. Now, that's what this actually equals. And you're thinking, boy, it must be a whole lot simpler to compute this than to do all this. And of course the answer is yes. But now you see what I've written here. You're accustomed to seeing the integral sign and the function and the dx, but you're not accustomed to seeing these limits. That's one thing we haven't covered yet. That's what we call a definite integral. When we don't have the limits, we just call that an indefinite integral or an antiderivative. And so what we're going to find is that all of this nice summation process, together with the technique of computing antiderivatives, will actually come together to create the fundamental theorem of calculus. And we are done.